So in the last time we looked at a standing wave in a string, right? When the end of the string were fixed. What do you think about the wave we would have in a column of air, vibrating column of air? Example would be like a flute, right? Like there is air that passes when you blow a flute, air passes in through the column, right? So what kind of standing wave do we get if we have vibrating column of air? Okay, so let us see. There are several possibilities, but we'll do general version. One is one end open, basically. Okay, so let us do open, close tube. Okay, so I'm gonna make here open. This side is open, this side is closed. Okay, let's say this has the wavelength L. Now this part I'm just gonna write here a little bit. So what happens is this part is open, so the pressure here is really atmospheric pressure here. Okay, so this region here, I'm gonna make a diagram here maybe, so I think that would probably be good. So let us say this is like our X. Okay, this is our origin here. And then this point here we have what pressure is going to be some value of atmospheric pressure P atmosphere, okay, ATM at this point. But then so this is kind of right, so it's so as you blow, what happens, the molecules are gonna get compressed and really squeezed together, right? They will get really compressed, and then what happens, they get compressed all the way, but then the air, right, goes from here all the way, they get compressed here. By the time it hits the bottom, what happens? By the time it hits the bottom, now it is going to come back, reflect back. Okay, wave is going to reflect back. See, a very similar concept. It's a different here, like, but then the concept of reflection of the wave happens. That's how we get the standing wave in a vibrating column of air. Okay, so the wave would these molecules, right, air molecules, they kind of get compressed, and then they, by the time they reach here, they kind of also get like rarefied. By the time it starts to get reflected, right? So it's kind of like this. So compression, rarefaction happens, but then by the time it gets to the end is basically really, once the wave reaches to the bottom, it has no place to go, so it has to return back, it has to reflect back. When it starts to reflect back, then the molecules are going to rarefied, meaning it will create a region of lower pressure region, okay? So, and then it's gonna come just out here, I mean it's gonna get to this side. So there is a maximum change of the pressure, not just the pressure, but the change in the maximum change of the pressure happens at this end, okay, in comparison to this end. So whenever there is a maximum change of pressure happens, what happens? The molecules are going to vibrate with a higher amplitude, right? So this end, that's why, so this end we can say, since the molecules are vibrating with largest possible oscillation, really here it is oscillation, it's better to talk about oscillation, we can label this side the end, okay? So this is the end, this is the open, this is the close, I mean to say close end, this is the open end, okay? So at the close end we can say that that's where the maximum oscillation of the molecules are occurring, so we can consider that as the NT node, okay? So this is the important part. And then this point here, it's open to the atmosphere, the pressure cannot really change there, so that's almost like a fixed point in the string, okay? So this point we would make a node, so remember how we make a node. So this wave kind of goes there, by the time it reaches there, it kind of gets there, and then it has to reflect back. I wanted to draw it like, so it comes back like this and it comes back. Okay, so what do you guys see here? So this is what this shape of the wave, we have for open closed tube. Now if you look at, right, like a graph, this is where we have a lambda, right, wavelength, one wavelength. This looks like almost like up to here. Does it look like up to here? Almost look like this. So this length here corresponds to a wavelength lambda by 4. Okay, so here for open closed tube, length L is equal to lambda by 4. Okay, which means lambda equal to 4 times L. This is when we have just one antenna there, right? So now if we keep changing the number, we can just derive this and then generalize. This is for, let's call lambda 1. Okay, now we can generalize, and for some lambda m, we can write this as 4L divided by m. Okay, where m equal to 1, 2, 3, and so on. Alright, so this is the wavelength of the wave that is traveling in a vibrating column of air, traveling in a tube with one end closed and one end open. Okay, I have written only open. Closed tube means one of the end is open, one of the end is closed. It doesn't matter. You can also close this one and make this side open. It doesn't matter. Okay, so this is the case. Now it turns out that the overtones are given by frequency Fm is again multiple of fundamental frequency F1 here. Okay, F1. Okay, so where F1 is what? V, F equal to V by lambda 1, right? Which is equal to V over our lambda 1 is what? 4L, right? Okay, 4L by M equal to 1, so really, okay, so this is what we have here, F1. So if you look at M, multiple M would be just multiplied by that M quantity. Okay, alright. Wait, did I do this right? 4L by M? Yes, it's right. Okay, so frequency, overtones are given by, they are the multiples of the fundamental frequency. Wavelength is given by 4 times the length of the tube divided by m. Okay, alright guys, so now next part we would look at the both ends either closed or open. Okay, and let us see how does that change from what we have here. Okay, so now let us look at let's make this open or closed at both ends. Okay, this is also called open or closed tube. Okay, so using the same concept, if it is open at both ends, what do we make? We can make a tube like this, right? A flute, right? Like this. Okay, like a length. So this is just L length. And then just by the same convention, since these are the open end, the air pressure, the pressure here is really the atmospheric pressure. So, and this is also atmospheric pressure, so it's not possible to, change pressure here drastically, right? So those are again just like the end fixed for, string, okay? So So here we, in that region is going to be, since the pressure, there is not much change of pressure here, we will label that as a node, right? Because node means where the molecules are not, where the molecules have a least oscillation, basically, right? So so if it is the open tube, then what happens is the wave, right? So it goes like this, gets there, and then the other part comes like this. Okay, I'm going to try to draw it much a little bit nicely. Okay, like that. Okay, so the two ends here, these are the node here. Alright, now if you look at this, kind of looks like half of this wavelength, right? Like this half. So this L is really, this corresponds to lambda by 2. Okay, so for open, the tube with both ends open, we can write lambda by 2 equal to L. Okay, so in essence we can write lambda equal to 2L. Let's call this as lambda 1, right? We have only one of the antinode here. So if we keep doing this, we find that lambda m equal to 2L by m. See, this relationship is very similar to what we get for a standing wave in a string, okay? Similar. Mathematically they are similar. Now physically they are different, right? In terms of physics. So mathematically they have a same equation, 2L by m. And then, so F1, we can write F1 equal to what? B over lambda 1, which is what? B over 2L, right? And then it turns out we can write Fm equal to just m times F1. Okay? So the overtones are again the multiple of the fundamental frequency, F1. Okay? So important thing, you have open tube at both ends. Okay? So you have here node. This is something you would want to remember. How you remember is think in terms of the pressure difference. Okay, pressure cannot change, which means at this end, which means the molecules cannot oscillate with large oscillation. So that must have the minimum oscillation. So it means that is the node. Okay, and then wherever the molecule can oscillate with maximum pressure, then wherever the molecule can, oscillate with maximum oscillation, those regions are antinode. Now think about it, if we had a closed tube, what happens? Instead of this end, it won't be node anymore, it would be antinode, right? It would be like half of the end, this part like half, like end. Like what we did earlier in the, open closed tube, okay? Alright guys, so this is about the standing wave in a vibrating column of air. Let us see, 1, 2, 3. Oh, I didn't write this. I do need to write this one. Where m equal to 1, 2, 3. And so, oh guys, I just remember. M equal to, what did I write? I don't remember right now. Okay, I'm gonna make this, okay, here. Separately, this is, I don't remember what I wrote earlier since I don't have it here on my board. For open, close tube, m, this value of m is not 1, 2, 3, 1, 3, 5 and so on, okay? So please make this, changes. I don't know what I wrote earlier. This is actually, the difference is because this m has to be the odd number here, okay? Not the even number. The even number cannot be included when one end is like open and one end is closed, okay? So this m equal to 1, 3, 5 and so on. So this is for open tube. beautiful. Alright guys, so that's about this standing wave in a vibrating column of air.